funny, but
That's crazy. Yeah, I was dealing with them yesterday. I emailed them, just having issues. It's not technical stuff, just figuring out my schedule. And they sent me also a passive aggressive email, but
yeah.
got it figured out. Hopefully I don't know. That's messy happening right when people are trying to register.
Yeah. Well, and
It's having trouble with the portal?
Yeah, the portals, I'm getting a bunch of emails right now. I was supposed to register like 15 minutes ago, and when I went in, even though my registration time was open, it said that like registration was closed. And so I emailed the registrar, and they just sent out an email to everybody saying that the portal's down for all 5 of the schools.
All right. Yeah, that explains things, because I just tried to approve a bunch of perm requests and I can't get into the portal either. Yeah.
Yeah. Yeah. So my apologies. I'll be registering probably during this class, but as soon as it's back.
Yep, no problem.
Do you have any idea if the classes are going to be online next semester?
Nobody knows. That's the big $1 million question. Nobody knows. Yeah, it's a good question. Maybe online for part of the semester, the whole semester. Nobody knows.
Kind of hard registering for the classes, not knowing that.
Yeah.
Registering for a lab class, not knowing if I'm gonna have to do the lab online or.
Yeah. It's a big question mark. It's kind of terrible. It'd be really nice if we knew something. Amber, I see your chat. That's fine.
Okay, cool.
Let's see. All right, let's see if I could share my screen successfully. Having internet trouble, so I'm going to try using the cable again, which takes longer to set up, but I think is more reliable once it's working. Anybody have any homework questions?
I had one on number 13.
13? Remember that?
Yeah, for part C about, like, it was like sketch the level sets. And then I wasn't sure how to do it for a Lyapunov system.
13. Yeah, let's go over it. X squared minus y squared.
Yeah.
If my iPad will ever show up. At some point we'll see it. It'll just magically appear. It'll just take time. Oh, something just happened. No, nothing just happened. Y'all see anything? Let's try it again.
Just a blank white screen.
Okay. We'll just wait a minute. Technology issues. Give more people a chance to show up anyway. Still nothing. All right, I give up. Let's do it with over Wi-Fi. I can share my screen with a direct connection or through Wi-Fi, and the Wi-Fi seems to be slower, but easier to set up. All right. Now it's going to take me a minute to reconfigure my screens. And I got to resume. Okay. We're in business. All right. Yeah, let's go over number 13. Bad color. 13, we've got g of x, y equals x squared minus y squared. What is the gradient system with vector field given by the gradient of g? Okay, how'd you do that?
I just took the partials of g with respect to x and with respect to y, and I got 2x and negative 2y.
Perfect. Great. Classify the equilibrium point at the origin. Yeah, so if you set this equal to 0 and this equal to 0, obviously there's just one solution, which is that x comma y equals 0 comma 0. So there's only one equilibrium point. They didn't even ask you that. So I think they assumed that was obvious. But now they're saying classify that equilibrium point. And it's just a linear system. This isn't even a nonlinear system. So the partials are 2, 0, 0, minus 2. And that's a diagonal matrix, so it's easy to read off the eigenvalues, 2 and minus 2. So what kind of equilibrium point is that?
Saddle.
Yep. Okay. Sketch the graph of G and the level sets of G. So I think they're assuming here that you remember what the graph of G looks like from a multivariable calculus class. If you don't, this is for everybody. I mean, we're trying to graph G of xy equals x squared minus y squared. So there are some techniques from calculus that you might remember. For example, you can graph just the xz plane and the yz plane by setting the other variable equal to 0. So if you want to know what's happening in the yz plane, you set x equal to 0. And so this is all z. So if we set x equal to 0, we get z equals minus y squared, which is just a downward opening parabola. So in the yz plane, it just looks like a downward opening parabola. And in the xz plane, so this is for the yz plane, the xz plane, you set y equal to 0, and you get z equals x squared, which is an upward pointing parabola. So in the xz plane, in this plane here, we see an upward pointing parabola. And then in the xy plane, you set z equal to 0, and you get the equation x squared minus y squared equals 0, which means x squared equals y squared, which means y equals plus or minus x. So that's two lines in the I'm going to try to draw the, so there's the xy plane, and I'm going to draw the line y equals x and y equals minus x. So hopefully that's all starting to look a little bit familiar to you. I'll redraw it outside of this. You can also look at level sets, which is exactly what you end up having to draw eventually in the next part of the problem anyway, what the level sets are. So level sets, for example, the level set where z equals 1 gives you the equation x squared minus y squared equals 1. You could solve that for y, and you get y squared equals x squared minus 1, or y equals plus or minus the square root of x squared minus 1. If you just wanted to graph that, y equals plus or minus square root of x squared minus 1, there's lots of techniques here. There's no x-intercept, right? If you set x equal to 0, you get an imaginary number. There is a y-intercept. If you set y equal to 0, you get plus or minus 1. And the other thing to notice is the asymptotes. As x goes to infinity, this minus 1 starts to matter less and less and less, and you just get the square root of x squared. So the bigger x is, the more this just looks like y equals x. So here's y equals x, and it looks like that. And again, it's plus or minus. The small, so another solution is y equals minus x, which looks like this. And as you go off to negative infinity, kind of the same logic applies. You get this thing and that. So it's just a hyperbola. X squared minus y squared equals 1 is just a hyperbola. That's what you're seeing at height 1 in this three-dimensional picture. So I'll keep trying to draw it, and the picture's just going to keep getting messier and messier. Up here at height 1, we see these hyperbolas oriented in the y direction. So they look kind of like this and this. These two hyperbolas. Picture's getting messier and messier. I'll just try to like jump to the final answer now. This is just a typical answer for a saddle. Just some basic ones from Calc 3 you should know, like z equals x squared plus y squared is an upward pointing paraboloid. Z equals minus x squared minus y squared is a downward pointing paraboloid. And then the saddles, there's two equations for a saddle that are come up in Calc 3. Xy is one, and the other one is x squared minus y squared, or y squared minus x squared. And they all look kind of similar. They have, they look sort of like this. And there's this sort of X in the middle here. And on the sides, there are these hyperbolas going up the side. And there are these hyperbolas here going down the other way. If you look at the top view, which is exactly the next part of the problem, so you put your eyeball here and look down, what you see is these lines, y equals x and y equals minus x. Those are the level curves where z equals 0. And when z equals 1, we drew the picture up here. This is what you see where z equals 1. So you see a hyperbola here and a hyperbola here. Those are the two level curves you get when z equals 1. If z equals 2, it just kind of opens up. And when z equals minus 1, now you're going down in this picture. If z equals minus 1, and you see these hyperbolas, and z equals minus 2 will give you those hyperbolas. So kind of typical picture of the level curves of a saddle look like that. So that just, again, I've taught Calc 3 for 20 years now, so it's relatively easy for me to just kind of spit that out. But you guys have only seen this a couple of times. Maybe it's been a couple of years since you've had Calc 3. Hopefully this is jogging your memories, but this would be a challenging problem if you didn't already know the answer, for sure.
So for sketching level sets, do we just set like z equals different values and then, oh, okay, cool.
That's exactly right. That's it. Yep. That's how you set level sets, is you just draw one picture of the XY plane, and then you draw a bunch of curves corresponding to different values of z. Yep. Then they say sketch the phase portrait. This isn't the phase portrait because this is a gradient system. So the phase portrait are the curves that are perpendicular to these. And what's interesting about that is here's a curve that's perpendicular to everything, and here's a curve that's perpendicular to everything. And this is a curve perpendicular to all those curves. You end up actually with the exact same picture, just rotated 45 degrees, which is an interesting fact about saddles. That the level curves of a saddle are the same as what you get if you draw the curves that are perpendicular to those. So the blue stuff, all those blue curves are perpendicular to all the black curves. And that's just another picture of level curves of a saddle. So those blue curves are the solution curves of the original equation, going all the way back up here. The solution curves of this equation, the whole point is that those equations come from a gradient of a function, and the solution curves of this system are going to be always perpendicular to that. And so the blue lines are the phase portrait of that gradient system. For those who haven't done it, let's look at 14, and we're just going to jump to the answer. It's 14. So at number 14, the function is g of xy equals x squared plus y squared. I already said up top, that's just one of the ones you should know from Calc 3. That's a paraboloid. If I were to slice that paraboloid with horizontal slices, what would the picture be of the level curves?
Won't the level curves be circles?
Yep, just a bunch of circles. If you think about this, you just get circles. Yep. And so looking straight down on that picture, you see circles. This is what the level curves of a paraboloid looks like. And now what are the curves that are perpendicular to those level curves? How do we find those? Perpendicular curves that are perpendicular to all those circles? What do they look like?
The gradient.
Yeah, the gradient. What do they? What just describe to me the picture? If I were to draw on a bunch of curves perpendicular to these circles, what do they look like?
They'd be pointing towards the center, right?
Yeah, they just look like radii. And it's not clear if they're pointing toward the center or pointing away from the center. That's something actually also up here. To really draw the phase portrait, we'd have to put arrows on those blue curves. And we haven't done that yet. We can do that by looking back. Let's go back to problem 13 for a second. Now, I want to put arrows on these blue curves. I'm going to go all the way back to my original system, where I see 2 is the eigenvalue in the x direction and -2 is the eigenvalue in the y direction. So in the x direction, we have a positive eigenvalue, so things are expanding. And in the y direction, we have a negative eigenvalue, so things are shrinking, which means in the x direction, things are moving away from the origin. In the y direction, things are moving toward the origin. And now you can kind of fill in the arrows everywhere else, just to be consistent with those. Okay. Same thing over here. If I want to know if the arrows go away from the origin or toward the origin, well, now it does help to actually do a little bit of the work. It won't take long. The system is dx dt equals 2x, dy dt equals 2y. And I think it's fairly obvious that both those quantities get bigger as time goes on, right? That's going to give us the linearization there, gives us the matrix 2, 0, 0, 2, which has eigenvalues +2, +2, which means everything is going away from the origin. So we have a classic picture of a source. That's 14. I wasn't asked about it, but it's nice to compare 13 and 14. 13, you've got this kind of classic Calc 3 equation of a saddle, and you get this picture in the end. And in 14, you have this classic equation of a paraboloid, and you end up with this picture. There's actually a deeper reason why both 13 and 14 are important. And that is because every system, especially every gradient system, but actually this is true for every differential equation, around the equilibrium point, you can linearize it. That would be a first degree approximation. So remember from Calc 2 that any function can be approximated by a linear function. That's actually Calc 1. But you could also approximate functions by a quadratic. It's a better approximation, okay? And then you can think about Taylor polynomials where you can approximate it by a cubic or quartic, and you can even take that limit and use an infinite degree polynomial. But a second degree approximation for a function is usually pretty good. And in fact, the dynamics, the picture, the phase portrait around the equilibrium point is completely determined by the second degree approximation. So when you zoom in on an equilibrium point, another way to think about what's going on there is to look at the second degree approximation. And the second degree approximation is just going to look like one of these classic Calc 3 pictures. You're just going to see a paraboloid or a saddle. That's really all you can see, right? Paraboloids will correspond to sources or sinks, depending on if they point up or down, and saddles correspond to saddles. So that's why all you see with these gradient systems is saddles or sources or sinks. Lots of interesting math there. Lots of interesting stuff to talk about. Any other homework questions? I think there's only one or two others that I had assigned. Good? All right, let's move on then. I think today, last time I said we would do 5.5 and 5.6 today. That's ambitious. I think all I want to do today is 5.5. And all I want to do from 5.5 is just work through one single example. That's it. Okay? But I think it may take us the whole time because it's not exactly an easy example. But I think it gets the whole point across of the whole section 5.5. So back in chapter 3, we were just looking at linear systems, and we spent almost the whole chapter looking at two-dimensional linear systems. So there are two variables and you have two equations. And then in the very last section of chapter 3, we talked about linear systems in 3 or 4 or 5 dimensions, higher dimensional linear systems. And we got these pictures where we could see, for example, if we had a 3-dimensional system, x, y, and z, here's a simple 3-dimensional system. dx dt equals 2x, dy dt equals 3y, and dz dt equals minus 2z. Okay, about the simplest possible 3-dimensional system you can imagine. So things in the phase portrait, things are going to move away from the origin in the x direction, away from the origin at a different rate in the y direction. Okay, so in the xy plane, you see these kind of parabolas doing this. Oops, that arrow is backwards. Okay, but in the z direction, things are moving toward the origin. So it's some sort of like hybrid saddle and source. In the xy plane, you have a source, but in the xz plane, it looks like a saddle. In the xz plane, I draw the x, here's the xz plane. Hopefully everybody can see that. In the xz plane, we have these hyperbolic curves. Everybody kind of see what's going on there? I know that picture's a bit of a mess, but you see this classic sort of hyperbolas in the xz plane and also in the yz plane. But in the xy plane, you see, maybe I'll draw them separately. So here's the xy plane, here's the xz plane, and the yz plane. And in the xy plane, we're seeing kind of these classic, it's like a source. But in the xz plane, we see this. And the same picture in the yz plane. Oops. So there we've got two positive eigenvalues and a negative eigenvalue. We can also have something like, I'm just trying to jog your memory, we can also have a system where you have, in the xz plane, it looks like a spiral source. Right? So things look like they're spiraling away from the origin in the xz plane. But in the yz direction, it looks like a source also. So things in 3 dimensions will look like they'll kind of spiral up around that axis, going up away from the z-axis and upward. And actually this picture isn't great because the coils of that spiral should space out more and more. It should be rising faster and faster and faster as it goes up, right? or you can look at situations where you have a negative eigenvalue along the z-axis, but a spiral source in the xy plane. So then things will move downward along the z-axis. And as closer you get to the xy plane, the more you're spreading out. Hopefully this looks familiar from what we did about a month ago when we were in chapter 3. And that last section of chapter 3, it was three-dimensional linear systems. My pictures aren't as good as the ones in the book. Feel free to go back to your book and look at those pictures. All right, thanks, Michelle. I got a thumbs up. Awesome. All right, now the idea is just to combine, take that kind of work and bump it up to nonlinear systems in 3 dimensions. So we've spent all of chapter 5 thinking about 2-dimensional nonlinear systems. So let's look at a 3-dimensional nonlinear system. And the only analysis that's going to carry over, we're not going to look at null Kleins, we're not going to look at Hamiltonian systems or the Lyapunov systems. The only thing we're going to do is just linearization. So for 3-dimensional nonlinear systems, we really only have one technique that works, and it doesn't even work great because we're going to get these 3-dimensional pictures that are going to be really hard to draw. I'm going to spend the next half an hour or so just working on just one such system, try to work through the details of it and try to draw it. And then we'll look at a computer version of it to try to get a better feel for it. And all you can do is just keep drawing pictures, different views, different perspectives, different pieces of it, and then just try to somehow chunk it together in your head. And even the computer version, since it's 3-dimensional, is complicated. So it's a little bit hard to see what's going on. But once you've done the work, the math, the arithmetic, the calculus, and you've attempted to draw a bunch of pictures, and you've looked at a computer, once you've done all those things, you really can start to get a real feel for what's going on. So the only technique we're going to do is just linearization. That's it. So all we're going to do is find the equilibrium points and linearize around each equilibrium point. And what we'll get near each equilibrium point are these kinds of pictures up here, right? These kinds of 3-dimensional pictures are exactly what we'll get. But we'll get each of those pictures around each equilibrium point. So we can have an equilibrium point that looks like, we can have one equilibrium point that looks like this, another equilibrium point in the same system somewhere else where things look like this near that one, and then a third equilibrium point where things look like this near that one. And then to try to put this all together into one picture obviously can be very, very, very difficult, okay? So let's just try it for one particular system. This is a really famous system. Some people would say this system is gave really birth to an entire field of mathematics called dynamical systems, which is often in popular literature called chaos theory. So this one system really gave birth to what we now call chaos theory. It's called the Lorentz system. Was first studied by, let's see if I can do this from memory, for a guy named Edward Lorenz in the 1960s. I want to say like 1963. I think he was working for Bell Labs at the time. I'm not sure. And he was a meteorologist studying weather patterns. So he was trying to come up with a really simple model of weather systems. It was just a 3-variable model. I don't know what the variables represented. And there were different, you could play with the constants involved. We'll use the following constants, dx dt equals, we'll use 10, you can play with that 10 to get other systems, but the general form of the Lorentz system looks like this, dy dt equals, again, you can play with that 28 as much as you want. It's an 8. Okay, so there's a 3-dimensional system, and we're gonna look for the equilibrium points, and the math is the same. Set them all equal to 0, try to simultaneously solve them and find values of x, y, and z that make all 3 equations simultaneously equal to 0. once we do that and have those equilibrium points, then we can linearize by just finding a 3x3 matrix of partial derivatives at each equilibrium point. Then we're going to find the eigenvalues of that 3x3 matrix at each equilibrium point, and the eigenvectors. These are going to be three-dimensional things, so it's going to get complicated, right? The characteristic polynomial is going to be a degree 3 polynomial, right? So let's just try to work through it, and if we get really, really bogged down in the details, we can just kind of jump to the answer that's in the book. But let's try to work this through by hand as much as we can, okay? We'll kind of try to do it together. So we're going to set each equation equal to 0. So that first equation is particularly nice. That first equation tells us, obviously, that y has to equal x. Right? So now let's look at the other two equations. This equation here gives us 28x minus, now the original equation was minus y, but I know y equals x, so I'm just going to make that substitution right off the bat. Minus xz equals 0. That's nice because now there's an x in every term. Well, you can make that 27x minus xz equals 0. You can factor out the x. And that tells us that x, whoa. Why did that just jump? No idea why that just jumped. That tells us that either x equals 0 or z equals 27. Okay, fair enough. All right, so I know y equals x, that's up here. And I know either x equals 0 or z equals 27. All right, so now we've got two possibilities here. So let's combine this x equals 0 equation with this first equation up here. And that gives us minus 8/3 z plus 0 equals 0, so z equals 0. And in this case, x equals 0 and y equals 0, so we just get 0, 0, 0. If we combine this equation with this one, now we get, oh boy, we get minus 8/3 times 27 plus x, which we don't know at this point, times y. We at least know y equals x, so we can make that x squared equals 0. 8/3 of 27, well, let's see, 1/3 of 27 is 9, right? 9 times 8 is 72, so we have minus 72 plus x squared equals 0, so x squared equals 72. So x is plus or minus square root of 72. What the hell is 72? And I feel like I did something wrong. What did I do wrong? (72) is 9 times 8. Oh, square root. So that's it's also.
It's 36 times 2.
Thank you. The square root of 36 is 6, so we get plus or minus 6/2. Thank you. Okay, and again, y equals x. So we get 6√2 for x, 6√2 for y, and we get 27 for z. And we also get minus 6√2, minus 6√2, and 27. So we have 3 equilibrium points. Good. 3 equilibrium points. All right. So now we got to compute the Jacobian and evaluate the Jacobian at each of those equilibrium points. They're a little bit messy. 27 is unfortunately a relatively big number. 6√2, we've got some roots in there. It's a little messy, but c'est la vie. We'll do what we can. All right. So let's see. We want I think the partials are going to be pretty easy. So the partial of the first equation with respect to x is minus 10, and with respect to y is just 10. So we have minus 10, 10, 0. So minus 10, 10, 0. Sorry to keep flipping back and forth. I wish I could show them both at the same time. What's the partial of the second equation with respect to x, y, and z? With respect to x, we get what? 28 minus z. That's the partial with respect to x. Partial with respect to y is minus 1, and the partial with respect to z is minus x. 28 minus z minus 1 minus x. 28 minus z minus 1 minus x. I think that's right. Okay, and then the last one, partial with respect to x is y, partial with respect to y is x, and the partial with respect to z is minus 8/3. So yx minus 8/3. Yx minus 8/3. Did I lose y'all? How we doing? Feel like I'm just babbling. Okay, good, Amber. I got a thumbs up. Yay. All right. Now, again, we've got these 3 equilibrium points up here. So let's deal with 0, 0, 0 first. And then we have the matrix minus 10, 10, 0, 28, 28, minus 1, 0, 0, 0, minus 8/3. Okay, there's something beautiful about that, which is that we have this 2 by 2 block on the diagonal and this 1 by 1 block on the diagonal. And that is a system which decouples. So what we're seeing is in the XY plane, it just looks like the behavior of that 2 by 2 matrix. And on the Z axis, it just looks like we have this eigenvalue of minus 8/3. So one of the eigenvalues is obvious. The eigenvalue in the 0, 0, 1 direction, in the Z direction, is minus 8/3. We just have to find the eigenvalues in the XY plane, and the eigenvectors in the XY plane. And to do that, we just have to analyze this matrix minus 10, 10, 28, and minus 1. Does everybody understand that? So normally, if we had a 3 by 3 matrix where none of the entries were 0, just have 9 different numbers there, we'd have to actually write down a degree 3 characteristic polynomial, and it would be pretty messy. And we may have to do that when we get to the other 2 eigenvalues. Okay, but so the other 2 equilibrium points. But at least at 0, 0, 0, we don't have to do that. 0, 0, 0, we have, we can just tell from the form of the matrix that lambda equals minus 8/3, and that's corresponding to the eigenvector 0, 0, 1. We're just going to look for the eigenvector in the XY, the eigenvectors and values in the XY plane, and there we just have this 2 by 2 matrix. So let's just do it. Minus lambda, that gives us minus 10 minus lambda times minus 1 minus lambda minus 280, oh Lord, which is, what do we get here? 10 lambda squared plus 10 plus 10 lambda plus lambda is plus 11 lambda minus 280 equals 0. Lambda squared plus 11 lambda minus 270 equals 0. God, I wish that factored, but I don't think it does. A little bit messy. At some point, we might whip out a calculator and just get decimals here. And I'm also going to cheat a little and peek at the answer. I don't even think it says the answer. I don't know what the answer is. So let's just do it. Let's keep going here. So lambda, whoa, stop that. So lambda is minus 11 plus or minus the square root of b squared. 11 squared is 121 minus 4ac. Okay, well, c is negative. 4 times 270 is, anybody know it? Otherwise, I'm going to cheat. 4 times 270. Not that using a calculator is cheating. It's 1080. All over 2. That's minus 11 plus or minus. I'm going to cheat. I'm going to just use decimals here. So we've got 1080. We've got a calculator up. Plus 121 is 1201. And then we're going to take the square root of 1201 and get 34 point, about 34.6. So about 34.6 over 2. So that's, well, we get a positive value and a negative value. We get, let's see, 34 minus 11 is about 23, about 20, oh, just do it. Let's see, 34.6 minus 11 divided by 2 is 11.8. And 34.6 plus 11 divided by 2 is 22.8. Those are pretty big numbers for eigenvalues, right? This means this system is really going to push things away from the origin in 2 directions in the xy plane, but we're going toward the origin, right? This is negative on the z-axis. So it is kind of like one of these generalized saddles. It's a lot like this picture way up here, where you're going toward the origin on the z-axis and away from the origin in 2 different directions in the xy plane. So it looks like a lot like that picture right around the origin. All right, I don't think we need the eigenvectors so much at this point. We know we're going to be pushed away from the origin in the xy plane and toward the origin along the z-axis. I think that's all we need for now, okay? So it's might be called some sort of 3-dimensional saddle. All right, let's look at the other equilibrium points. So again, let's go back to this matrix I got. I'm just going to copy it again. Minus 10, 10, 0. Minus 10, 10, 0. 28 minus z minus 1 minus x. 28 minus z minus 1 minus x. Yx minus 8/3. Yx minus 8/3. And we'll just do one of the other 2 equilibrium points. And I think just the signs just flip when you do the other one. So the equilibrium point we're doing is 6 root 2, 6 root 2, 27. 6 root 2, 6 root 2, 27. And that gets us the matrix minus 10, 10, 0. 28 minus z, well, that's nice. 28 minus z, z is 27, so we just get 1. Minus 1. Minus x is minus 6 root 2. And then 6 root 2, 6 root 2, minus 8/3. Oh boy, okay, so around this equilibrium point, 6 root 2, 6 root 2, 27, we do have a 3 by 3 matrix, and it's a 3 by 3 matrix that we now have to work through this characteristic polynomial. The characteristic polynomial is going to be a cubic, and let's give it a shot here. So it's going to have 3 roots, and they're kind of ugly. So I think at this point, no one in their right mind would expect you to be able to do this. And the authors of the book clearly didn't do it by hand, because I'm peeking ahead at the answers to the book, and they're giving decimal approximations. They almost certainly went to a computer algebra package. So you'd have to like learn Maple or Mathematica or one of these packages and be able to just type this in. There are lots of online things. Wolfram Alpha is online. You should be able to just type in a 3x3 matrix into Wolfram Alpha and ask it for the eigenvalues, and it should just spit them out for you. In fact, let's try that. Let's try that. I haven't used Wolfram Alpha in years, but let's just try it. So I should share that screen. Oops, Zoom. I'm going to share my Wolfram, my desktop too. Share. Okay, hopefully you're all now seeing my second desktop here. And I already typed in Wolfram Alpha. Let's try it. Let's see what happens. I don't know how you type in a matrix in Wolfram Alpha. Does anybody know?
If it's anything like the Mathematica language, you have to do like, I think the way it goes is like you do square brackets and then you do each column in parentheses separated by, or sorry, each row separated by, I'm gonna Google it right now.
Yeah, Google it. Yeah, let's just do it. I'd rather not just pull out the answer from the book, because I'd like to show you ways where you guys can find the answer. And Wolfram Alpha is a totally reasonable thing to go to at this point. Algebra. Let's look at some of their samples. Let's see if they have equation solving, rational functions, finite groups, oh boy, matrices. Oh, here we go.
Trying to find a determinant, right?
We just want the eigenvalues. So right there, it says eigenvalues, and you type it in, it looks like with curly brackets with commas separating the rows and columns. Okay, there we go. So we want the eigenvalues. Oh, wait, is that in parentheses? Eigenvalues, no, I don't need parentheses. Just type in the word eigenvalues. Okay, let's just try it. Eigenvalues, there we go. Curly brackets, and we got minus 10, 10, 0, minus 10, 10, 0, comma. 1 minus 1 minus 6 root 2, 1 minus 1 minus 6 times, I'm going to guess it's just this, square root 2. Hope that works, comma. 6 root 2, 6 root 2, so I'll copy that. Oops, go far enough. 6 root 2, 6 root 2, and then minus 8/3. Let's keep our fingers crossed, see if this works, and enter. Ooh, it's thinking. Thinking. Hey, look at that. It's beautiful. At least it formatted it correctly for sure. And look at those eigenvalues. Minus 13.85. Minus 13.85. I'm writing these down, comma. Plus or minus 10 point, let's call that 10.2i. Oh, wait. Sorry. Minus point, let's see, about 0.09 plus or minus about 10.2i. All right. Hope I haven't lost you all. Back to my iPad. And whoop, didn't want to do that. Screen mirroring, zoom. Okay, hopefully you all are seeing that. Oh, you're not seeing that because I just messed it up. Okay, all right, so there we go. Minus 13.85 and 0.09 plus or minus 10.2i. All right, so in one particular direction, we have minus 13.85. I don't know which direction it is, but we're about to find out. And in some plane that is at an angle to that direction, we have this pair of complex eigenvalues. So in this direction, it looks like it's a sink. So things are going to go toward the equilibrium point. It's not toward the origin anymore, it's toward this equilibrium point in whatever direction corresponds to the eigenvector for minus 13.85. What about 0.09 plus 10.2i? What kind of, in that plane, what kind of thing is that?
Spiral source.
Spiral source, yes, source because the real part's positive. One thing to notice though is that that real part is really small, which means it's going to spiral away from the origin, but very slowly. It spirals out very slowly. The relative magnitude of some of these numbers is really surprising, right? This is a really strong sink. So things get sucked onto that plane really fast. And then once they're in that plane or close to that plane, they spiral away from the origin very, very slowly. So there's this equilibrium point. There's this direction where everything goes towards some plane very, very fast, right? And once you get near that plane, you start to spiral away from the equilibrium point very, very slowly. Okay, so the relative measures of these things is really important to understand. Okay. Let's look at, I wonder, going back to Wolfram Alpha, I'm not going to switch screens just yet. If I switch the word eigenvalues to eigen, oh, it already said corresponding eigenvectors. It did say that. It told us the eigenvectors were, I don't know if this is going to help us. The eigenvector here is about minus 2, minus 0.81, roughly. Minus 2, 0.81. Minus 2.81. So that's the direction that gives us a vector which determines a line. And the line in that direction is the line on which we're shrinking. That doesn't really help us quite so much. Okay. Let's try to put some of this information together. All right. So we've got, by the way, you get the exact same answer for the eigenvalues and eigenvectors at the other equilibrium point. I'm not going to work through it, but the exact same eigenvalues at the third equilibrium point. So at the third equilibrium point, there's also a direction where you're getting sucked toward a plane, and once you're near that plane, you spiral away from that third equilibrium point. Okay, so you got to think of what's happening. I'm going to say it. I'm going to wave my hands. So just look at my little tiny video here, and then I'll try to draw it on the iPad screen, and then we're going to look at a computer version. Okay, so here's my little video. I've got these two equilibrium points in space. Okay. And there are these two planes at each equilibrium point that are at some angle to each other, okay? And in those planes, things spiral away from the equilibrium point, okay? Now, once they get near enough to the other one, they get sucked toward the other one by its negative eigenvalue, but then they start to spiral away from that equilibrium point. And those spirals get bigger and bigger and bigger until they get close to the other equilibrium point where they get sucked toward that plane by that negative eigenvalue, and then they start to spiral away. So you can start to get some sense that something funny is going to happen here. As you're near one equilibrium point, you start to spiral away from it until you get close enough to the other one that you get sucked into it, and then you start to spiral away from that one. Okay, and you get some really interesting behavior here. So let's actually just look. Let's jump right to the computer model. So let me share my screen there. Let me share and look at it. So hopefully you all are seeing that. So there it is. And you can really see what we're seeing here is just one solution trajectory with starting at the initial condition minus 1, 0.1, 0.1. In fact, let's make that even minus 0.1. Doesn't really change a whole lot. So we're starting down at the very bottom of the picture. That is very close to 0, 0, 0. Now, if you remember, 0, 0, 0 was a, I'm now looking and going back, 0, 0, 0 was a source in 2 directions and a sink in 1 direction. So there's this plane on which things move away from the origin. You can kind of see it there. I wish I can scroll down. If you just focus down at the bottom of the screen there, where we started, that's the origin. And we're going to be shot away from the origin in some plane, okay? And we're going to be shot away. And when we're up here, we're going to start to feel the influence of one of these spiral eigenvalues, but we're going to be kind of pushed away from it, away from it, away from it, away from it, until we come over. Do y'all see my mouse? So I'm trying to follow this curve, and it goes down, 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 down. And now we're starting to feel the effects of the other equilibrium point that sucks us toward this plane. You can see all these spirals. We're looking at it kind of head on here. Right here, you can see this is all these spirals kind of lie in this plane centered around one of the equilibrium points, right at the center of those spirals. We get sucked toward this plane, but once we're near that plane, we start to spiral away from the origin, away from that point, away from that point, until we get close to the other equilibrium point. And then the other equilibrium point again, we get sucked into this plane. And then in that plane, we're going to spiral away from that until we jump over to the other one. So you get this amazing behavior where things kind of go back and forth and spiral away from one till they jump to the other, and spiral away from that one till they jump back to the first one. And it is extremely unpredictable. And that's why, as I said, it's kind of the birth of people studying what's popularly known as chaos. Because even though this is a deterministic system, there's no randomness to this system, it's also completely unpredictable. There's no way to determine in advance which of those two sides, which of those two equilibrium points you're going to be spiraling near at some number of time units in the future. It's just kind of, it is apparently going randomly from one to the other to one to the other, spiral around one maybe 100 times before it jumps to the other, spiral around there twice before it jumps back, and then a few times and then it jumps back. And there's really no way to determine how many times it's going to keep spiraling around before it jumps to the other side. And it really looks like completely chaotic solutions. The solution curves, actually now I do want to go back to my iPad screen. So we're back in my iPad screen. So in 3 dimensions, we had X, oh, that was terrible. Totally missed on my X-axis. X, Y, and Z. And we have this one equilibrium point at the origin, another equilibrium point at 6 root 2, 6 root 2, 6 root 2, 6 root 2, comma 28. So it's up here somewhere. And then another one at minus 6 root 2, minus 6 root 2, 28. So that's over there in the back of the picture. And things kind of spiral around this one, spiraling out until they get sucked into this one, and then they spiral around that one until they get sucked into this one, and it kind of goes back and forth like that. That was sort of the picture we got, and it keeps going back and forth. If we look at, for example, if we look at a graph of Z with respect to time, the Z coordinate is going to keep oscillating around this value 28, right? So up here at 28, it's just going to look like these oscillations right around 28, and they're going to be fairly random. What's more striking is if we look at x versus time, because the x-coordinate of one of these points is positive 6 root 2, and the x-coordinate of the other point is negative 6 root 2. So if I look at the x-coordinate with respect to time, sometimes it's going to be oscillating around positive 6 root 2, and sometimes it's going to oscillate around negative 6 root 2. And what you'll see is it looks like these oscillations around here until the oscillations get big enough, and then it jumps to oscillations around here, and then up to here, and then down to here. And every time it flips from one side to the other, you see this graph at the bottom is going to flip to oscillations around 6 root 2 versus oscillations around minus 6 root 2. And there's this flipping back and forth is very, very unpredictable. There's some other features of this system called sensitive dependence on initial conditions. It's a long term, and that is the technical term for chaos. When people say the word chaos in the popular press, the mathematicians use the phrase sensitive dependence on initial conditions. And what that means is that if your two different solutions are the tiniest bit off, so I will try to illustrate that first on my iPad screen, and then I'll go back to this graphing program. But if I have an initial condition that's very close to this, it'll follow it fairly closely for a little bit of time, and then it might jump over and then jump back, and then after a while it's going to be completely uncorrelated. So it doesn't matter how close you are to begin with, as long as you're not equal, those two solutions will look totally different. Let me see if I could jump back over to my graphing screen and show that to you. So you're all seeing the original solution that I posted. And now, let's get rid of this one. Let me copy this. Oops. You want to play with this, by the way, and you have a Mac. All Macs since like the 1980s came with this program, but it's buried. It's not in your application folder. It's in your utilities folder. And Apple's just kind of left it there. It's kind of funny. Like there's this old graphing calculator application that they left on Macs, basically unchanged since like 1990 or something. And I use it all the time. And I think other people do as well, which is why they've just never bothered to mess with it. All right, so I've got the same system twice here. I don't know if I can, I wonder if I can color code things. I should be able to. What I'm gonna do on the second one is I'm gonna vary the initial condition just by a tiny bit. I'm gonna make that 0.1 in the y coordinate, I'm gonna make that into a 0.2. Okay, and now we're seeing them overlapping. Let's see if I can change the color. Oh yeah, awesome, I can change the color to red. All right, so down there at the very, first of all, right at the very beginning, at the very bottom of the screen, you see the origin. And one of them got shot one way and the other one got shot the other way. So obviously they're gonna do very different things. Let's see if I can change things a little bit. Let's make that 0.1 and make this 0.11. Oh, the color went back. That's annoying. Okay, that's good. All right, now look at the bottom of the screen there at the origin. At the origin, they look like they're completely overlapping. Within the accuracy of the computer, you really can't tell down there at the bottom any difference between the red and the blue curve. Okay, and as we go up, you still can't. It almost looks like it's alternating color because they're right on top of each other. Even as we come all the way around, they look like they're identical. But sometime later, eventually, those two solutions are going to diverge from each other. And then eventually you see, like by the time we get over here, wherever this is, that the red curve and the blue curve are pretty well separated. And by the time we get over here, I don't know where this is, but there's a red curve here, and there's not a blue curve anywhere near it, right? Because the red curve and the blue curve, after some amount of time, are really doing just completely different things. Sometimes this is in the popular press. This has been called the butterfly effect. You might have heard of that. The butterfly effect is this sort of thought experiment where you go back in time to the prehistoric era and you kill a butterfly that's flapping its wings. So that changes the air currents around that butterfly, which will eventually, which changes the initial condition of the system from that point forward. And that changes all the weather patterns from that point forward. And eventually the weather patterns, which affect the history of all living things, changes, and the life on this planet may look completely different from that point forward, even though you've made this tiny, tiny, tiny change to the initial condition. All you did was remove one butterfly from the system. It's called the butterfly effect. I don't know who coined that term. All right, so it's 12:07, time for us to stop. So again, I'm gonna suggest you do some of these problems in 5.5. I'll be honest with you, I'm not gonna test you on this in the final exam, because I think to do these problems, you really are gonna need a program like Wolfram Alpha to help you find eigenvalues and eigenvectors. And obviously it's very, very hard to take the final information if you have 3 equilibrium points with different behavior around all 3, and then try to put that into a 3-dimensional picture is extremely difficult. You know, do your best. It's worth making that attempt. And I would just suggest kind of looking through. There's only 8 problems in section 5.5, and I think even among those 8, they only give you one. The first 4 problems are all about one system. So exercises 1 through 4, they give you a new system, and then they say, exercise 1, they tell you one of the equilibrium points of that system, and then they ask you to do all the linearization around that point. Exercise 2, they say, hey, here's another equilibrium point for the same system, now do it again. So basically, exercises 1, 2, 3, and 4 are just the 4 equilibrium points for that original system that they give you. So I would try that. Just try it. Just try problems 1 through 4. So they give you a system, and they say in problems 1 through 4, analyze the equilibrium point at these 4 different equilibrium points. Find the Jacobian, find the eigenvalues and eigenvectors, classify the equilibrium point, sketch the phase plane space near that equilibrium point of that linearized system, and then discuss in a few sentences what happens to a solution with initial value near that equilibrium point. There are several cases depending on which populations are non-zero. You need not consider negative populations, but consider all combinations of 0 and positive populations that are near the equilibrium point. So basically, just think about what happens to solutions. And I'm happy to talk about this in class next time. Next time in class, my plan was to jump into 5.6 and then do chapter 4. And I'm considering doing that in the opposite order. We may jump back to chapter 4 and then do 5.6. We only have 2 more class days, just Monday and Wednesday of next week. So we're not going to cover all of chapter 4. And 5.6 and chapter 4 are closely related to each other. So we may somehow do everything together over 2 class days. And there's some interesting behavior there that I kind of just want you to see. There's a famous case of the Millennium Bridge in London that when it opened in the year 2000, within a few hours, they had to shut it down because the oscillations of the bridge were too extreme. And then that was the year 2000, and that is explained in chapter 4. And then at the end of chapter 4, they also explain the Tacoma Narrows Bridge, which was a bridge that back in the early 1900s, a similar sort of thing happened. Shortly after they opened the bridge, it was subjected to oscillations of a different kind of oscillations. And those oscillations got so extreme that the bridge collapsed. So there's some videos online of both those things happening. So we're gonna look at those videos, and then we'll do the analysis and see why did each of those bridges collapse for these different but related reasons. And I think that'll be a nice way to end the class, to show you these extreme examples of why good engineering is so important. Any questions before we go? You good? All right, all. I'll see you all on Monday next week.
Thank you.
Bye.
Thank you.
Yeah.
Thank you.